here's some basic notions like sample space, probability function, event. And I formulated 3 simple axioms of how probabilities can be manipulated. And then I also formulated one particular model, which is called equiprobable model. So there, each point in the sample space occurs with the same probability. So in equiprobable models, you have everything you need to start calculating probabilities. And I'd like today to start with one concrete example, which hopefully will illustrate to you the power of these formal axioms and all those rules we introduced in the last lecture. So it's a historical example. In the early days of probability theory, people were keenly interested in it because they were interested in gambling, and they wanted to find some patterns, some rules which would allow them to win when gambling. And there was one gentleman who lived in France, and his name was De Maire. He lived in 17th century, and he observed in 17th century that it is more likely to obtain a 6 in 4th rows of a single die than obtain a double 6 in 24th rows of 2 dice. Okay, so he observed that it is more likely to obtain a 6 in 4th rows of a single die than to obtain a double 6 in 24 throws of 2 dice. It was an experimental observation. I'm not quite sure whether he probably did both, watch many games, and then did experiment himself by throwing and writing the frequencies. And he thought that that's a paradox, because the way he thought about calculating probabilities was, well, surely probability is proportional to the number of throws or the number of attempts. And surely it should be inversely proportional to the number of possible outcomes in each throw. Right? We're interested only in one outcome, so 1 out of that many. The more you have outcomes, the less likely it should be. So if you looked at the fraction of number of throws divided by the number of possible outcomes in each throw, and he observed that in the first experiment, when we have 4 throws of a single die, the fraction is 4 over 6, right? So we have 4 attempts and 6 possible outcomes in one throw. While if you do the second experiment, you have 24 throws or 24 attempts, and the number of outcomes in a single throw is 36 now, because you throw double dice, right? So you have 6 times 6, 36. And these two numbers are the same. So you thought it's weird. It's a paradox that if you observe it, one is smaller than the other. And so what I'm going to show you is how to calculate the two probabilities using the rules I formulated on the last lecture. So we'll be using the equiprobable model, using the equiprobable model. And for the first experiment, we we have the following sample space. I'll call it S1, the first sample space. So we're throwing a single die 4 times. So the outcomes will be 4 integers, and 1, and 2, and 3, and 4, such that each n sub I equals 1, 2, 3, 4, 5, or 6. You can describe it like that. And the number of points in the sample space is just 6 times 6 times 6 times 6, right? For each choice of the outcome. And that's the same as 1,296. 1,296, right? So that's the sample space. The model is actually probable. Each point out of this 1,296 carries the same probability, which must be 1 over the total number of points, 1 over this, right? And what we're after an event, I call it E1, right? It's a subspace in the sample space, in which at least 1/6 is present. So E1 is the following event. At least 1/6 is present among N1, N2, N3, and N4. So to calculate the probability P of E1, we have to calculate the number of points in this event and divide by the total number of points in the sample space. So it's a counting problem. And we have to count all 4 tuples of integers, each between 1 and 6, in which at least 1/6 is present. And I'm going to use that simple trick of counting complementary configurations. Calculate that. So I have 6 times 6 times 6 times 6 points in the entire sample space without any restrictions on the number of 6's. And I should subtract from that all the number of configurations in which 6 doesn't occur. It's very simple to count those because, okay, for N1, N2, N3, and N4, I'm allowed to use numbers only from 1 to 5, right? I'm not allowed to use 6. So I have 5 choices for the first outcome, 5 for the second, third, and fourth. So that gives me this number. And so that's just by counting, right, using the elementary counting rules. And I divide by the total number of points, which is, again, 6 times 6 times 6 times 6. I can rewrite this expression. If I divide by the denominator each of the terms in the numerator, I get 1 minus, and 4 5s divided by 4 6's can be wrapped up into 5 over 6 to the power 4. Okay, just more succinct. And using a calculator, you find that this number is approximately 0.5177. You can already observe that, well, the guess of the gentleman was 2/3, which is approximately 0.66. So it's already a different number from that. But let's now look at the second experiment and calculate the probability and compare and see which one is larger than the other. Okay, so for the second experiment, we have a different sample space. I'll call it S2. So that consists, each time we throw, we have 24 attempts, and each time we throw 2 dice, so the outcomes will be a pair of integers. So N1, M1, this pair will be the outcome of the first throw, and then N2, M2 of the second throw, and so on up to the pair which represents the outcome of the 24th throw, right? And here these integers, mi and m sub j, I can collectively call them like that with using indices, should be 1, 2, 3, 4, 5, or 6. So this is my description of the sample space S2. And the event he was interested in is at least one double 6 is present. So E2 can be described by this condition: at least one pair 6, 6 is present among N1, M1, comma, N2, M2, comma, dots, N24, M24. Okay, and the probability then for this event should be the number of elements sitting in that subspace divided by the total number of points in S2. So the total number of points in S2, right? That's so in single throw of 2 dice, the number of possible outcomes is 36. And since I have 24 such throws, the total number of outcomes is 36 times 36 times 36, 24 times. And I can write that product more succinctly as 36 to the power 24. So that's the total number of points here. To calculate the numerator, we'll use the same approach, right? We will take the total number of points and subtract those configurations, those points in the sample space for which we don't have a double 6 occurring in any of the 24 attempts. So how many configurations are there like that? Well, in each throw, I'm allowed now to have only 35 possible outcomes. I just remove the double 6, which is 1 out of 36 possible outcomes, right? And since this happens, this is the number of choices in each of the 24 throws, the total number of such configurations is 35 times 35 times 35, 24 times, which again I can write as a power 35 to the power 24. So that's the number of configurations I want to remove so that at least one double 6 occurs, right? So those are all with no double 6 occurring at all. So the difference is the number of those in which it occurs at least once. Again, I can rewrite this in a nicer form as 1 minus 35 divided by 36 taken to the 24th power. And if you use a calculator, that gives you 0.4914 and so on. And that number is indeed smaller. So P of E2 is indeed smaller than P of E1 we calculated for the first experiment. And it's interesting to note how small the difference is. It's just, two digits in the second position, right, plus decimal point. So it's remarkable that he was able to notice such a small difference. But yeah, that's the modern way to explain that observation, which that gentleman thought was a paradox. Any questions on this example, please? So the equiprobable model is very widely used. It's sort of the most popular model, although it's not the only one. We will talk about at least one other model later this week. And I'll have more examples on using the equiprobable model, but for now, I want to come back to the axioms I formulated, and then show you, well, first I will prove some more consequences from these axioms, and then I'll show you how one can use these axioms to calculate probabilities, not even specifying a particular probability model. Right? So some facts are so general that they apply to any probability model, equiprobable or not. So here's a reminder. What were the axioms? They were very simple. The first one said that for each subset of the sample space, P of E is a number between 0 and 1. And the second axiom said that P of the empty subset is 0, and P of the entire sample space is 1. And the third axiom said that for any E1 and E2, for any two events, such that E1 intersection E2 is empty, the probability of E1 union E2 is probability of E1 plus probability of E2. Okay? So if you have non-overlapping events, then the probabilities just add up. Note that the sample space in the context of a probability model can be used as a universal set. S plays the role of the universal set because all events are subsets from the sample space. So we can define complement E bar for any E subset of S. So the following general consequence of the axioms I'll formulate as a theorem, and that theorem says that the probability of a complement is 1 minus probability of the original event. So we can illustrate this by events diagram. So let the square be the entire sample space, and we have inside it our event E, and outside it we have event E bar. So it follows that the entire sample space can be represented as a union of E and E bar, because any point is either inside E or it's outside, and then it automatically belongs to the complement. Moreover, E and E bar, they don't intersect by definition. Again, the intersection is the empty set. Therefore, by axiom 3, P of S equals P of E plus P of E bar, right? Since they don't overlap, the probability of the union is the sum of the probabilities of each one. And moreover, by axiom 2, P of the sample space is 1. By axiom 2, P of S equals to 1. Therefore, 1 equals P of E plus P of E bar. And then moving P of E to the left-hand side, we obtain the formula for P of E bar. So it's 1 minus P of E. Okay, so it's a simple general consequence of the axioms. another general statement. Theorem 2, it says that for any arbitrary events, A subset of S and B subset of S, the probability of the union equals probability of A plus probability of B minus probability of A intersection B. And you can recognize here the inclusion-exclusion formula for the number of elements, except for the number of elements is replaced by the probability. If we had an equiprobable model, then each probability here would be given by the number of points divided by the total number of points in the sample space, and then this formula would follow from the inclusion-exclusion formula directly. But this formula applies more generally, not only for the equiprobable model, right? It suffices for these three axioms to be satisfied for it to hold. So that's what it says. How do we prove this? So again, we will draw events diagram for these two events, which now may be overlapping. Here's A, here is B. So here in the center I have A intersection B, and then the part of A which is not in B can be written as A minus B, and the part of B which is not in A can be written as B minus A. Then, by axiom 3, I can represent A as a union of A minus B and A intersection B. And these two subsets of A, they do not overlap, right? So the probability of A equals the probability of A minus B plus the probability of A intersection B. And the same I can do for P of B. B is a union of A intersection B and B minus A. And by definition, they do not overlap. So the probability of B is then the probability of B minus A plus the probability of the intersection, A intersection B. This is certainly true. Also, we can write the union A and B as a union of three non-overlapping sets. So it's A minus B to the left of the intersection itself, A intersection B, and B minus A. And these three sets, they do not overlap, right? All their pairwise overlaps are empty, and therefore by axiom 3, which you can apply twice, right? You can first say take the union here and consider it a single set and apply it to the two parts, and then apply it one more time. So you don't really need a special axiom for 3 sets, 4 sets, and so on. You can use the basic axiom many times. So then it implies that probability of the intersection is the sum P of A minus B plus P of B minus A plus P of the intersection. Okay, then now I can, well, proceed to prove my formula. I can, for example, I can use the first two expressions, add them up, and subtract P of A intersection B. So the right-hand side, RHS, the right-hand side of the formula we want to prove can be rewritten as, so for P of A, I'll substitute the expression above. So P of A minus B plus P of A intersection B. For P of B, I'll substitute the second expression I derived, P of B minus A plus P of A intersection B. And what else stands on the right-hand side of the formula in the statement of the theorem is minus probability of A intersection B. Here we have two terms cancel out. And what remains is exactly this combination, which we know is the same as P of the union. That equals P of the union, which is the desired left-hand side, right? Left-hand side. So I showed that starting from the right-hand side and rewriting it using these substitutions, I can rewrite it as P of A union B, which stands on the left-hand side. So in this proofs, we're using this, these three axioms, and to summarize these axioms very succinctly, you can intuitively think of probability as having properties of an area. So imagine that you have different regions on the plane with different area. If they don't overlap, then the total area equals the sum of the areas of the two subsets. Well, if they overlap, you can manipulate with different pieces, same way as you would manipulate with area. So when solving these types of problems, where only general axioms are used, you can always draw Venn diagrams and think of the probability as an area. Right, so those were two general consequences which always apply. The inclusion-exclusion formula for three sets also can be generalized to arbitrary probability function, but we're not going to really use that formula, so I'm not going into that. So let's instead look at some other examples in which we will only be using the axioms. Here's an interesting example. If P of A is equal to 2/3, P of B equals 3/4 in some probability model, in some unspecified probability model, what is the largest P of the intersection B can be, and what is the smallest possible value? Two questions. Great, so largest and smallest. So here, I will use, in the solution, we will use one other simple consequence of the axioms, again, which follows immediately if you think about areas, that if A is a subset of B, then the probability of A is less or equal than the probability of B. Right? So bigger sets have bigger or equal probability. Again, it can be simply derived, right? But I'm not going to do this thing, but essentially it's you know, it's a simple property following from the axioms again. So coming back to my example, how can we think? So let's first address the question: what is the largest value? All right. I know that this set A intersection B, that sits inside A. It's a subset of A. Therefore, I can immediately conclude that the probability of A intersection B must be less or equal than P of A, which is given, 2/3. Okay. But also, I know that A intersection B sits inside B. Therefore, I can conclude that the probability of A intersection B is less or equal than probability of B, which is given to be 3/4. So both conditions must apply. So the strongest condition here corresponds to the smaller probability, which is 2/3. So based on what we are given, based on the information we are given, the largest possible value of P A intersection B is 2/3, right? Because both conditions must apply. That's definitely smaller than 3/4. And can it really happen that this 2/3 is achieved? Yes, it can. It can happen. For example, if this value can be achieved if one possible situation is that A intersection B is the same as A, and there was a tutorial question in tutorial 1, like what does that mean? That actually means that A sits inside B. So it's equivalent to saying that A is inside B. A sits inside B, and then the probability of the intersection is the same as probability of A. Right? So this can happen. It's not just an estimate. And it cannot be bigger based on this consideration. What about the second question? The second question is what's the smallest possible value? Well, you can think about this problem intuitively. So imagine that I have these two sheets of paper, and one represents the set A, another one represents the set B. So they probably overlap somehow. And to make the overlap as small as possible, I want to pull them apart. But there is a constraint. They all sit inside the sample space, right? At some point, I cannot pull them apart further because they will fill in, the union will fill in the entire sample space. But when that happens, certainly the overlap is the smallest, and it must have the smallest probability. So that's the intuitive explanation of what's going on, but how can we proceed more formally? Well, we can use that theorem 2, the formula derived in the theorem 2. So by theorem 2, we can rewrite the probability of the intersection just by rearranging the terms. We'll move P of the intersection to the left and P of the union to the right. So that's P of A plus P of B minus the probability of the union. And P of A and P of B are given and are fixed. So it's 3/4, so 2/3 plus 3/4. Right? So the only thing here we don't know is the probability of the union. And it comes with a minus sign. So the larger this unknown probability is, the smaller the probability of the intersection is. But the largest it can possibly be is 1. No probability is greater than 1. So this is greater or equal than 2/3 plus 3/4 minus 1, which gives you can bring this to the common denominator and obtain the value of 5/12. Okay, so when this probability is equal to 1 is exactly the situation I was showing before, right, when the union fills up the entire sample space. Okay, so that produces this value, and it answers the question. One thing we can conclude, well, this overlap is, we don't know much about it, but definitely it's not empty. Because if it was empty, then its probability would be 0, but the smallest possible value which is allowed by the general rules is 5/12, right? So that's the smallest value, so 0 is excluded. Definitely there is some overlap, and its value is between 2/3 and 5/12, right? So that's as much as you can extract from the two numbers we were given. Questions? So, making sense to everybody? Okay, so here we have not specified the probability model at all. We're just using the general properties, right? The general axioms, and they produce these numbers. Another example like that. So a weather forecast based on some unspecified unknown probability model produced the probability of rain today to be equal to 30% or 0.3. And the same forecast produced the probability of rain tomorrow to be 0.4. And the probability of the rain today and tomorrow was estimated to be 0.2. Two questions. What is the probability to have rain today or tomorrow? Find probability of rain today or tomorrow. And the second question, find the probability that it will rain tomorrow but not today. Okay, so what do we have here? We have two events, right? And it's quite long to write the event, but saying that rain tomorrow, rain today. So I'll introduce a shorter notation. So let A stand for the event that it rains today, and let B rain tomorrow. And in the first question, in part A, we can now reformulate the question we're asked in terms of these two sets, A and B. What we ask is to find the probability of the union, because union exactly consists of events satisfying it rains today or tomorrow. So you're either in A or in B. And here we can use theorem 2 again, which is essentially this modified inclusion-exclusion formula. So it will give us probability of A plus probability of B minus probability of the intersection. So probability of A is the probability of rain today, that's 0.3. Probability of B, that's probability of rain tomorrow, which is given to be 0.4. And the probability of the intersection, that's the probability of rain today and tomorrow, when both conditions apply. And that's also given 0.2. So just using that formula, we calculate this to be 0.5 or 50% chance that it will rain on one of these days. So okay, that was part A, just a straightforward application of the theorem 2. Let's now address the second question, probability that it will rain tomorrow but not today. It's useful to draw this diagram. So A and B, right, that's the general situation. So rain tomorrow means we are in B, but not today, this means we're not in A. So we can shade the event we're interested in. Right? So we want the probability of the event represented by the shaded region. And we know that the entire B can be represented as a union of the intersection plus the shaded area. Those do not overlap. So P of B equals P of the intersection. And let's call this shaded area as a subset C. So plus P of C. And therefore, P of C is just a difference. P of B minus P of A intersection B. And the numbers, we've got them. Rain tomorrow is 0.4, and the intersection is 0.2, so the difference is 0.2. So that's the answer to part B. Okay, so more, you can have more sets and more different intersections, different events specified, but essentially you can manipulate the probabilities as areas and find, from the given data how you extract the probabilities that you need. Questions, please, about these examples? Yes?
Would questions like A, would it always refer to the exclusive OR?
Well, it's always, the logical OR. It's always a logical OR, which means either in A or in B or in both, right? Because it doesn't say only in A or only in B. No, throughout this course, OR is only understood in the sense of the logical OR.
So I would have guessed that would have been 0.7, 0.01 and 0.5 on.
Yeah, that's certainly the sum which stands there. But because they can overlap, it can also rain both today and tomorrow.
But they don't overlap, just one rain.
Yeah, it can rain both today and tomorrow. That's certainly possible, right? It can rain tomorrow, one event rain today, and there's an overlap. It might rain on both days.
So why did you remove it?
Right, that's how the inclusion-exclusion works. I mean, it's sitting in A, so we would be like double counting this intersection. So it's present in 0.3 and it's present in 0.4. So it's present twice. So we should remove it its value once.
Yeah, but the current time cannot be both today and tomorrow.
There's no reference to time here. I mean, there's no reference to current time. It's not specified, It's,
I wouldn't see how the two can overlap.
well, it can rain on both days, no? That's what it means.
Yes, I can write on both days, but that would be A separately and B separately.
No, it would be both A and B. You're both in A and B. A is rain tomorrow. Sorry, yeah. A is rain today and B is rain tomorrow. The overlap is when it is both raining today and raining tomorrow. Sorry, maybe yeah, we can talk more during after the lecture, but at the moment I'm just not not seeing how to help you and what's really the stumbling block here. I don't know. Anybody else wants to ask or comment on what's unclear in this example? Okay, so we can talk during the tutorials or after class. I'm happy to do it. But I have still 5 minutes left, and I have still a lot of material. So I'm going to start talking about conditional probabilities. So let's consider a situation, a model situation, so it's a motivating example. A fair coin, and a fair coin means that in which such a coin for which heads is equiprobable with tails. Right? A fair coin is tossed twice, and it is known that at least one heads was obtained. It is known that at least one heads, or H, was obtained. What are the probabilities of other events given this? What are probabilities of other events? So here we can put the original probabilities and the updated probabilities, which I'm about to define. We can put them into a table. And in the first column, I'll put my sample points. So we throw a coin twice. So I can have two heads, tails, heads, heads, tails, or two tails, TT. And then in the equiprobable model, each point is equiprobable, so each comes with a probability of 1/4. Suppose now, I want to modify these probabilities given this extra data. So it's known, right? So this is the extra piece of data that at least one H was obtained. So my updated probabilities, which take into account this extra piece of information, I'll denote by P of something bar A, where A stands for this event. So just make a note that A equals the event at least one H occurred. And then we know that we should therefore assign to the other, to this point, tails, tails, probability 0. So given this extra information, this probability is 0 now, right? Because it doesn't have any heads. And now, well, how you should assign the probabilities of the remaining 3 outcomes? Well, they were not distinguished before they had equal probability, and the extra condition that at least one H occurred also does not distinguish the 3 of them between themselves, so they should be assigned an equal probability. again, and that probability, those probabilities should add up to 1. So since only 3 events left, I should assign them to be 1/3. So this updated probability is called the conditional probability, and in general, P B bar A, right? A conditional probability is assigned by the following formula. So it's a ratio of P B intersection A divided by P of A. So how do you read this? It's the probability for B to occur given that A has occurred. Given that A has occurred. And so A has occurred, so for any event B, only its overlap with A matters for calculating the updated probability, right? And that's what stands in the numerator. So only the part of B which is inside A should be retained. And the division by P of A guarantees that the updated probabilities add up to 1. Because, for example, if B is equal to A, right, A is your new sample space. If B is equal to A, then the probability with this denominator, we get A intersection A over P of A. A intersection A is the same as A. So we get P of A over P of A, that's equal to 1. Okay. So that's the general rule, and you can see that you will recover the 1/3 in the previous example if you take the previous probability 1/4 and divide by the probability of A, which was 3/4, right? Because this is A, all 3 of them, they have probability of 3/4. So 1/3 equals 1/4, which is the old probability, divided by 3/4. Okay, right. Time is up. So sorry.